Chan, Benny. I'm a bioinformatics engineer at 3 Billion. 3 Billion is a rare disease diagnostics company based in Seoul, South Korea. And today I'll be presenting our results from the challenge. The content itself, I've prepared it so that everyone could easily understand. So bear with me for 15 minutes. Jake has already introduced the task, but to more briefly introduce what we did, the goal was to identify novel and under-recognized symptoms and expand the definition of rare disease. We were given the symptom data of 741 patients who were diagnosed with rare neurodevelopmental disorders. And for the sake of combining all the data, we normalized all the symptoms into HPO terms and all the OMIM, all the diseases into OMIM or orphanet entries. So why is it important to expand the spectrum of phenotype data in rare disease? Right now, we're in the age of genome sequencing in order to diagnose rare disorders. However, it is still highly dependent on phenotype data, as rare disorders have very heterogeneous symptoms and not a lot is known about them. Knowing the full spectrum of phenotypes enables healthcare providers to connect seemingly unrelated symptoms together and then lead them to consider rare diseases in their differential diagnosis. So I would like to share a feature importance calculation done on 3Ask. 3Ask is our in-house model made with around 50,000 rare disorder patients. And what it does is it basically recommends and prioritizes variants that are causing the disorder. And what we wanted to check was what feature contributes most to the model in diagnosing a patient. And then the results showed that symptom similarity was the most influential factor of this model in providing an accurate diagnosis. And symptom similarity is basically the similarity between the patient's symptom and the disease symptom. So higher the symptom similarity means that this patient is like shares very similar phenotypes with the known disease. So to achieve this goal, this task, we made 3 assumptions on 3 different perspectives and then made approaches accordingly. So this is our first assumption. It was recognizing the fact that manual curation is very limited. Even reputable databases such as OMIM lack comprehensive information due to the limitations of manual curation. I brought an example of OMIM number 105120, unfinished type amyloidosis. This disease entry was created back in 1995, but no symptoms were registered in this disease until August 2023, which was only 3 months ago. And the symptom data that was added to this entry were from publications from the past. So this means that we have the data on the diseases, but they're not registered in our known disease ontologies, which shows an underrepresentation of the phenotype data on the diseases. So to tackle this issue, we exhaustively searched through PubMed's database of over 35 million publication abstracts. So our goal was we wanted to see which genes, which diseases, and which phenotypes are included in all the 35 million publications. And this was done through natural language processing in 2 steps. The first step is tagging the keywords in the text to see. So we use deep learning pre-trained language models based on a model called Roberta. So it extracts unstructured text that is expected to be a biomedical entity. And on the second step, we normalize these keywords from step 1. So what normalizing means, if I explain easily, let's say we're talking about UCLA. Someone could just be saying UCLA. Someone could be saying oh, do you know the university close to Getty Center? Or someone could be saying, oh, the university in Westwood. So all these people are referring to the same entity, UCLA, but since everyone speaks in different languages and their expressions are all different, we needed to normalize all these different ways of writing these concepts into one unified normalized concept. That's what it's doing. So it requires a base ontology. In this case, we normalized all genes into HG and C, diseases into either OMIM or orphanate, and phenotypes into all HPOs. So through this process, we have all publications that are annotated with genes, diseases, and phenotypes. This is an example I brought. So let's say we have a text in PMID number X. Based on our first part, tagging keywords, it would recognize, our language model would recognize Weidman-Steiner syndrome as an expected disease keyword, KMT2A as an expected gene keyword, and etc. And on the second part, if we normalize these keywords into recognized concepts, Weidman-Steiner syndrome tagged from first part would become OMI number 605130. So basically, all the keywords from all the publications were stored in a database that we could use to explore. I don't think if it's the word's pretty small, but this is an actual query that I took from the database I constructed. And I searched for OMIM number 605130, which is the Weidman-Steiner syndrome. And if you can see, all the titles are publications dealing with the following disorder. So now that I have created this database, now I need to find potential new phenotype candidates. And it's relatively easy. I first find all publications that mention the disease and gene of interest. And then from all those publications, I extract all the phenotypes. And from these phenotypes, I exclude the known phenotypes that are already established in OMIM and orphanate and HPO. This leaves us with phenotypes that are mentioned in publications but not established in disease ontologies. So the remaining phenotypes were considered for validation to see there if they're really novel phenotypes of the disorders. So that was part one. A second method was, the assumption was, since in the field of rare disorders, we don't have that much patients. It could be just one. Therefore, the 741 patient data that RareX provided, that itself is meaningful data. So we wanted to use this data itself. That's why we wanted to see which symptom would be statistically significant to be highly specific to a certain disease. And there are many ways to suggest the significance of the feature. But in this case, we use Fisher's exact test because it's a simple yet powerful tool, calculation method in small data sets. So we basically calculated all the significance of the phenotypes in every diseases, and we extracted them for validation. The third method and the last method was using the mouse phenotype data to reveal undiscovered human disease traits. We use mouse models because they share genetic and physiological homologies with humans, and there are a lot of studies on them. So the figure on the flowchart on the bottom simplifies this method. We just wanted to connect each links so that we could see which symptom would be related to human disease. So we use human gene to mouse gene association data and mouse gene to symptom data from MGI. And then we use mouse phenotype to human phenotype data from UPheno to connect all the dots, and the resulting phenotype would be a potential candidate for the disorder. So by combining all the three methods I mentioned, we found 36 novel and under-recognized symptoms across 14 diseases. Since I used the data from the publications, They were all supported with clinical publications, and they were also further reviewed by our medical genetists. And among them, 25 were also found in rare X patient data, which means that the symptoms found in the clinical publications were also found in the patients. So this real-world evidence further validates our results. Here are a few examples of the results we obtained. Malformed teeth in FOXP1 syndrome, abnormal EEG and Coulon-de-Vries syndrome, constipation and Ogden syndrome, hyperactivity and Parkinsonism in XTX-BP1 related disorders. These symptoms were found in many rare X patient data, but none of them were recognized as an established phenotype in all the famous ontology databases. So let me quickly highlight two practical applications of the methods I introduced. In the first case, I tried to expand this method on the OMIM clinical synopsis text. And remarkably, we found 62,842 symptoms across approximately 7,000 disease entries, which equates to an average of 8.2 symptoms per disease entry found. So basically, there's a lot of data out there, but they're not organized or curated. So this showed that by leveraging this data, we are able to, and anticipating more patients to be recognized for differential diagnosis as rare disorders. And also we are able to expand our coverage of known phenotypes. And another case is an actual case from our company. Using the database I constructed, there was a publication on PROSER1. This PROSER1 gene isn't in OMIM, it's not in Orphanet, it's not in HPO, but there was a publication about a patient with a homozygous frameshift variant with symptoms of developmental delay and hypotonia. And fortunately, there was a patient in our company that showed the same genotypes and phenotypes with this publication, and he or she was able to be diagnosed with the following publication. So this yields opportunities for undiagnosed patients previously unrecognized. To share some of the limitations and room for improvement in our methods, we use abstract data only. So if you use full text data, we anticipate to collect more phenotype candidates. And in the second part, the statistical significance would be enhanced if we had more patient data. We had 741 patients. That's a lot, but 200 of them did not have any data to be actually used. So that was a bit, that could have reduced the statistical analysis. And on the third part, if we apply different organism models, it could provide us with more phenotype candidates. So as Jake introduced in the previous presentation, there are no ground truths of this challenge, but thankfully, using our clinical publications and the real-world data from RareX, we were able to validate these phenotypes a little bit more. So expanding our understanding of rare disease phenotypes with these methods, it not only improves accurate diagnosis by providing more information about the disease, but it also will open new avenues for drug discovery. This will expand drug indications and identify new targets, offering promising prospects for future medical treatments. So in our company, the slide's a bit cut here, but we're actually using these expanded data to diagnose more patients. And with more diagnosed patients, I firmly believe with more continuous efforts and collaboration, we will be able to provide hope and opportunities for rare disease patients out there. I would like to recognize our team members, Kisang, Namseok, and Yongjun, who have also participated with me in this challenge. And this concludes my presentation. Thank you very much. Hi.
Nice talk.
Thank you.
I have a question about
Mhm.
the kind of database you built, for lack of a better word, from NLP of abstracts.
Yes.
I think that's an interesting approach. I was wondering
Mhm.
if you tried any existing databases that link genes to diseases and symptoms,
Mhm.
and if so, what you felt like you gained over doing the abstraction yourself.
Okay. The reason I tried the NLP approach, like you mentioned, there are already existing databases. The famous ones could be ClinVar and HGMD, but they're all based on manual creation eventually. So it won't be able to reveal the hidden ones. So how they actually work is like they find keywords, look into the publication, and they curate it one by one. That's why I think there's a coverage difference between this method. So we wanted to find all the publications. So I think that was advantage by using the NLP method.
Did you try any databases that were not designed specifically for rare diseases, but have incidentally captured some of the symptoms as individual disease categories? I'm thinking of something like maybe just GeneNet or something where you could find some of the same phenotypes that you see in the rare diseases, even though it's not designed specifically for rare disease.
Well, I think that's a good idea. Our company is focused on rare diseases, so that's why I could have been a bit. Yeah, I think that's a good idea, and I can further check them when I get back to Korea.
Thank you.
Thank you.
Great talk, thank you.
Thank you.
I would like to ask about the different methods that you presented. So you have the NLP, then you have the Fisher's test,
Yes.
and you have the mouse human.
Yes.
And on one of your slides, you had the number of associations that you identify by these methods, and I was wondering how this works together. So whether they are iterative or whether they complement each other. I didn't really.
Oh, I wrote the numbers here.
You had 25 in the end, and then you had for the individual methods, you
Yes.
had, I think, 26.
Yes.
Yeah, it's you.
Yeah. Anyways, some of the phenotypes were found in both, all three methods.
I see.
Some were just in one. Two of them, some of them were captured in two methods. So I haven't put in the details, but if you are interested, I could give you more information on that.
Okay, thank you. Thank you. Very nice talk. Especially you actually help identify one of the patients. I have two questions. First one is how did you define it is novel? And the second question is did you ever compare what your results shows to those rare diseases databases held by like organizations such as NORD, that is rare diseases in United States or like Europeans database?
Okay, what was the first question?
First question is how did you define like it's a novel thing?
Okay.
You say you identify novel diseases.
Yes.
Syndromes.
So it was this part, like eventually once we have the candidates, we have to validate them, but we can't validate them in an automatic fashion. Our clinical geneticists have to search through all the available data. And then once we check them, oh, this wasn't mentioned in any of the known concepts, then we consider them as novel.
Okay.
And the second question?
Have you ever do any cross-reference check with all those like rare diseases organizations database like NORD? I think they have a 500 rare diseases database.
I think that question goes along with your question. I think that's something I should further validate through. But since in the field of rare diseases, HPO, Orphanet, and OMIN pretty much covers most of the information. That's why we only use the three. But with your question, I could further check them in the future. Thank you.
Thank you.